Okay. Um, we finished this, I think, at the end of the last lesson, but I'll just remind you again of the electronegativities because those are critical and extremely important to the overall properties that molecules have. So you might want to pay attention because where we're going right now is going to be about the starting place for Gen Chem 2. And all of the material that we're working on right now becomes foundational to the beginning of the second course. So be sure you can reproduce this pattern for electronegativities. And remember also the little rule of thumb that I told you. If it's not one of these first rows, no matter where the elements are located on the chart, no matter whether they're metals or non-metals, whichever one is closest to this right-hand side of the chart will have the higher electronegativity. And I've checked this out over and over again. I've not seen it published anywhere, um, but I did notice it from work that a colleague did at Western Kentucky. And I've never seen that. The only thing I've ever seen happen is they you might predict one is larger than the other if they're far down on the chart and close together, and it might turn out that they're equal. But I don't recall an incident where um, the order is reversed. So I think that's a really good rule of thumb to use. Um, okay, well, let's look at what's called the valence shell electron pair repulsion theory. Uh, because that allows us to predict how molecules will shape themselves around each individual atom in the molecule. And it'll allow us to predict bond angles and things like that. And then when we look at electronegativities, we can even predict the spots along a molecule that might carry a positive or a negative charge. And that's going to be really important when we get to Gen Chem 2, and especially also for organic. Um, there's really two ways to learn organic. One is to memorize everything, and you can do that. In Gen Chem 1, you can probably get away with it. I'm sorry, in Organic 1, you'll probably get away with it, but not in Organic 2. You're going to have to learn these principles and say if you want to figure out what product is going to form. Imagine this. You've got two molecules. I'm holding my hands up again. My left hand is one of the molecules and my right hand is the other one. If I imagine my thumb is an atom in the molecule that carries a negative charge and my palm carries a positive charge. Well, when I bring these two molecules together, what's going to happen is the negative charge on one molecule is going to be attracted to the positive center in the other one. That's where the bond is going to form, and that's how you're going to get the product of the reaction without memorizing it. So to lay that foundation is what we're doing right now. It's called valence shell electron pair repulsion theory, and we will go into great detail later on, but we need a part of it now, and we will just delve really, really deeply over our heads when we get to Gen Chem 2. All right, the VSEPR notation, or sometimes called VSEPR notation, is AXMEN. Now, A is a central atom that all of these M other atoms are attached to. E is the number of, it represents lone pairs, and N is the number of those lone pairs also on the central atom. So right off the bat, when we're looking at the VSEPR notation for an individual, for a whole molecule, you have to have a central atom. Now, the central atom is just the one atom in the whole molecule that every other atom is attached to. If you've got a long strung out molecule where there's not one atom that has all the others attached directly to it, this method doesn't work. It only works for central atom molecules. Like, for example, if I did carbonate, CO3 2 minus, well, the carbon atom has all 3 oxygen atoms attached to it. It's not COOO, it's 1 carbon with 3 oxygens attached, and then some lone pairs and stuff to get, maybe lone pairs, I don't think that one does, to get the charge correct. So right off the bat, we need to recognize the central atom. Now, the central atom, say I've got a bunch of molecules, like for example, I said carbonate. Well, carbonate, that's okay. Carbon is the unique atom in the whole bunch, and it's kind of easy to spot that as the central atom. But, you know, if you had 2 different atoms to choose from to determine which one's going to go in the middle, which one's going to be the central atom, it's almost always the least electronegative atom in the whole bunch, or the one that's more metallic, or if we're writing formulas, the one that's on the left. So anytime you've got a choice, pick the central atom as the one that is the least electronegative. And there'll be M of the other atoms, called X here, attached to it. And N is the number of lone pairs on the central atom. Now, so here's the kind of a bullet point method of going through how you would do it. First thing you're going to have to figure out is what is the central atom. And as I said, that's usually the least electronegative atom. Then all the others are attached to it. Now we have to determine the number of valence electrons in that molecule. Well, remember, for each atom, we can look at the periodic table and tell how many valence electrons we have. For the representative elements, and that's the first 2 columns and the last 6 columns, these are the only ones that's going to be important here. For those columns, the group number is the number of valence electrons. For example, if I've got a sulfur atom as my central atom, then I'm looking at sulfur on the periodic table is in group 6. So it would have 6 valence electrons. And then you add up the valence electrons for all the other atoms as well. So the group number is the number of electrons that come from the central atom. And then if it's got negative charge, you're going to add more to it. So like, for example, if I did carbonate, CO3 2 minus, carbon's in group 4, oxygen's in group 6. 3 of them would be 18 and 4 would be 22. And then when I would add 2 more for the negative charge, I get 24 electrons. So you add up all the group numbers and then add in the negative charge. What if it had been a positive ion? Well, you just subtract that many electrons from that total to get the total number of valence electrons in the molecule. Now, hydrogen, I'm going to show you a method that is not the one that's in the textbook. I will guarantee you it's much better. The method that most textbooks teach is to just take those valence electrons, put the molecule together, attach all the atoms onto it, put octets around everything by adding lone pairs, and then seeing if that's right. And if it's not right, try it all over again, do something else. Well, that's kind of an arbitrary way of doing things, and that's not the best way. I'm going to show you the best way. It's a mathematical model. It's not my own work. I'll tell you about the reference to it a little later. But it is the best method I've ever seen for doing VSEPR notations. It's a mathematically based method. And to make it work, we're going to try to see how many octets you can make out of the number of valence electrons you have. Well, hydrogen can't have an octet, right? So hydrogen can only pick up one more electron and make hydride ion, and then it would be like helium, or it could lose one electron and just be a bare proton, and it does that as well. So I think I've mentioned to you maybe before that hydrogen often appears in group 1, and it's certainly not an alkali metal, but it's put in group 1 because it reacts the same way that the alkali metals do to form H+ ions. In the periodic charts, when I was where you are, we also had hydrogen sometimes in group 7. And the reason for that is it does the same thing also that the group 7 ions do. Group 7 forms a -1 ion, and hydrogen can form hydride ion, a -1 ion. So what we do to make hydrogen work, if you've got a hydrogen in the molecule, like formaldehyde is H2CO. Well, the hydrogens are being counted as if they were in group 7 to do this octet rule trick. So if you want to, you can just pretend, for example, hydrogen is a fluorine. Do the structure for the fluorine molecule, and then when you get done, replace all the fluorines with hydrogen, and it'll still work. Except for lone pairs. Don't put any lone pairs around hydrogen. Okay, so if hydrogen is present, you count it as 7 valence electrons as if it were in group 7. Okay, now I said the objective is to find out how many octets can you make of that. And remember, the octet is a stable arrangement of electrons, and it's a good arrangement. And so to do that, you take the total number of valence electrons you've got and divide by 8. That will give you the number of octets that you can produce. And that's going to be the number of bonded pairs of electrons or the number of other atoms that are going to be bonded to that central atom. So in the VSEPR notation, that was the M. Remember, we had the general VSEPR is AXMEN. Well, the way you get the value of M is you take the total number of valence electrons and divide by 8. That is the value of M. Now, that might not use up all the electrons. So all the rest of the electrons have to be lone pairs of electrons on the central atom. The number of lone pairs on the central atom is what you get when you take the remainder. After you've divided by 8, you take the remainder and divide by 2. The electrons that are left over are going to be lone pairs of electrons on the central atom. Okay, so that's going to give us the N in the VSEPR notation. So at this stage, we have the VSEPR notation for that molecule, ion, whatever. And it'll be AXM. We know what M is now. We take the remainder, divide by 2, and we know the N. So we've got the entire VSEPR notation by doing this math. Now, we're going to build a structure. And the gist of the valence shell electron pair repulsion theory is that electrons around the central atom will repel each other. Whoop-de-doo, we knew that, okay? So they're two different kinds of electrons. There's bonded electrons and non-bonded pairs of electrons, just as you would expect. If you've got a bonded pair of electrons, what that means is that pair of electrons has 2 nuclei in it, one on each end. That's where the bond is between say if I did carbonate a while ago, carbon and the oxygen, there is a bond holding those together, a covalent bond that's holding them together. And so those bonded pairs, the bonds between the carbon and oxygen atoms, say in carbonate, are going to repel each other. So the CO bond and one of the CO bonds is going to repel the other CO bond. Now, it doesn't in carbonate. We'll see in a few minutes. I'm going to actually do that one for you. But if you had non-bonded pairs, well, the non-bonded pairs have one nucleus on one end, but there's not another atom, not another nucleus on the other end. So the bonded pairs expand and occupy more space. In other words, the maximum repulsion that's going to occur is between non-bonded pairs. So if that central atom has two pairs of electrons that are not bonded attached to it, those two pairs of electrons are going to push each other apart very much. And that'll be the biggest repulsion, will be between non-bonded pairs and bonded and non-bonded pairs. The next repulsion after that one is between non-bonded pairs and bonded pairs. So, for example, water is going to have two non-bonded pairs on it and two hydrogen atoms attached to it with single bonds, H2O. We've done that Lewis structure before. But the two non-bonded pairs on oxygen repel each other the most. So they're going to push apart from each other, and they'll be pushing now against the hydrogen to oxygen bonds. And that's going to push those bonds closer together because they repel each other less. So the bond angle in water is going to be pushed together a little bit because of these repulsions. So we're going to be able to look at very precise shapes around a central atom when we take these into account. Now, so if the central atom does not have an octet, now this is critical. When you do this, follow the math. When you calculated the number of octets and you divided by 8, if you got a remainder 0, that means there are no lone pairs on that central atom. And in the case of carbonate, that's what you will get. There won't be any any lone pairs on the central atom, but if I had just CO3, carbon, and 3 oxygen atoms, 3 CO bonds in that molecule, then I don't have any lone pairs on there, and so that's going to determine the shape that we would get for that. So if it doesn't have a lone pair, in that case, I would only have 6 valence electrons on the central atom. The book would tell you to add 2 to carbon. That'll be wrong. It won't work. It tells you to do that first, and then once you do that, see if it worked. And if you got the wrong number of electrons shown in your molecule, go back and put in double bonds. We don't have to do that. If our math says there's no electrons on the central atom, there are no electrons on the central atom, period. So that means to create the octet, you have to make a double bond, or maybe more than one double bond. You're going to have to add enough double bonds to create the octet on the central atom to the other atoms that are present. So you have to add some number of multiple bonds. You could have the double bond, that would be enough to do it, or you might have a triple bond, or in some cases, like in carbon dioxide, you have to have put two double bonds in. And so at this stage, we're just adding multiple bonds to the central atom to create the octet on the central atom. Now, you can't have non-bonded pairs on hydrogen either. So we're going to add non-bonded pairs to the other atoms to complete the octets around them. So if I'm talking about CO2, now I've got carbon fixed. I've got the octet on carbon. Now I'm going to look at the oxygen atoms and see how many lone pairs I need around those oxygen atoms in order to create the octet on them. So the only time we deal with non-bonded pairs is if, from the math, if the math says we've got some on the central atom, we put them in. The math says we don't have them on the central atom, we don't put them in. We deal with the non-bonded pairs then on the peripheral atoms, the atoms that's added and attached to the central atom. Now, at this stage, we check to see if there are other possible structures. For example, we will do carbonate in a few minutes. It's a good illustration here. But if there are other ways that you can arrange the electrons just by moving electron pairs around to the atoms on the central atom, if you can just move those electron pairs around to different places, then those extra structures exist. That's what's called resonance. And that stabilizes the molecules. So at this stage, what we would do is check the valence electrons to see that it's correct. And the book tells you to do that too, but then it tells you if it's not correct, go back and do something. If it's not correct here, you just missed it. Check your number of valence electrons, try again, and follow through the procedure. So when you add up all the electrons, there'll be 2 for each bond and 2 for each non-bonded pair. And when you add them all up, you make sure that you agree with the number of valence electrons that molecule has. Okay, again now, if we've got hydrogen present, we did the math pretending we were going to get an octet for it. We don't, and we don't put any electrons around a hydrogen other than the bonded electrons. Hydrogen is never going to have non-bonded pairs on it. Okay, let's kind of go through what we would need to do to work these kinds of problems. How many valence electrons does selenium have? Well, if you look at the periodic table, selenium is the element in group 6. We've got oxygen, sulfur, selenium. So all of those are group 6. So it has 6 valence electrons. If I wanted to draw a Lewis structure, remember how we did that? That was on your quiz. We would do 1, 2, first 2 go paired up, remember? That goes from the, that goes into the s orbital. Remember the valence shell on the outside is s orbitals and 3 p orbitals. The first 2 electrons go in the s orbital and pair up. The next electron would go into one of the p orbitals and would not pair up with anything else. The next electron would also go in a p orbital. The next one would go in a p orbital. Now we've just got 5 and we need 6, so we would pair one of them up in the p orbital. So if I'm looking at selenium, what I'm expecting it to have is 2 lone pairs of electrons and 2 places where it can bond. So, for example, if this is going to react with hydrogen, we would put maybe a hydrogen here and a hydrogen here, and we would have H2Ce, Se. Or we could put chlorines on here and here, or fluorines and here, and so forth. So we can build structures based on the Lewis dot structure that we've already done. Now, how many valence electrons would SOCl2 have? Okay, well, sulfur is in group 6, oxygen is in group 6, chlorine is in group 7, and we've got 2 of them. So that would give us a total of 26 valence electrons. So if I'm dealing with this molecule, SOCl2, and by the way, it does exist, it's called thionyl chloride, you'll use it in organic, kind of stinks and stings your nose. So be aware of it when you get to organic. Okay, 26 valence electrons. Now, arrange them in order of electronegativity. Well, if you look on the periodic chart, sulfur, oxygen's in group 1. It's going to be the most electronegative in that bunch, and then chlorine, and then sulfur. So if we arrange them, sulfur is going to be the least electronegative, and oxygen is going to be the most electronegative, and chlorine's in the middle. Again, if I'm doing a quiz or something like that, I'm going to see if this one was right. And every answer that this one is right on is one I have to continue to consider. But any answers that's got sulfur in the wrong place over here, then I can eliminate. And if I got sulfur in the right place for 2 or 3 of them, I'll look and see if oxygen is in the right place. If I find oxygen in the right place for one of them, I know I've got the answer. Chlorine has to be between them. And that's what it should show. But the relevance here is, if I draw this molecule, you see there's 2 atoms that are individual atoms and one with 2 atoms. Obviously, the chlorine is not the central atom, but it could be either one of these 2. Our rule said what? Central atom is the least electronegative. So even though I drew it SOCl2, that's not going to be the way it's bonded. The oxygen is going to be bonded to the sulfur, and the other 2 chlorines to the sulfur. Now, if I'm dealing with size, now, this is an example that has charged species. And if you look at each one of these, all of them have the same number of electrons as neon. So you've got magnesium +2. Magnesium's in group 2A. When it loses 2 electrons, it has an electron designation just like neon. Sodium's in group 1. When it removes 1 electron, it becomes like neon. Fluorine's in group 7. It gains 1 electron to become like neon. Oxygen's in group 6. It gains 2 electrons to become like neon. So all of these have an electron configuration of neon, noble core, neon. Now, which one is bigger? Well, let's think of it this way. Let's do the smallest one first. The smallest one, they've all got 10 electrons in their valence shell, but magnesium's got 12 protons. So 12 protons pulling 10 electrons are going to pull them in tighter than 9 protons in sodium would pull the 10 electrons into it. Fluorine or oxygen, when we get out here, oxygen is going to gain 2 electrons, and it's going to have 8 valence electrons totally, and it's going to have 10 electrons around it. That's going to be the biggest one. So it goes as charge. If they are what we call isoelectronic, that is, if all these species have the same configuration as the central atom, then, or as that middle one in this case, neon, then it goes as charged. The +2 ion is the smallest, the +1 is next, the neutral is next, the -1 is next, and the -2 is the largest. And again, if I'm doing the comparison, I'm probably going to get the smallest and the largest first, because that's an easy comparison. And again, if this is a quiz or an exam, then I'm going to find the answers that have these 2 in the correct place. If there's only one, I'm already done, you know. I will answer and go on. Okay. All right. Now, here's some problems that we're going to do. And I'm going to illustrate the VSEPR notation with them. And here is hypobromous acid, HOBR or HBRO. It's written both ways. Let's see how many valence electrons. Now we're going to fib right here. We're going to say hydrogen has 7. It doesn't. Oxygen has 6, and bromine has 7. Hydrogen can be in group 7, just like bromine is. We've got a total of 20 valence electrons. Okay, I take the 20 and divide by 2. I get 16. The remainder is 4. So there's going to be 2 atoms attached to the central atom. There they are, 1, 2, attached to oxygen. Okay? Now, the remainder is 4. And if I divide the 4 into pairs, I get 2. So the VS-EPR notation is AX2E2. Now, that's true for this molecule here. But the beauty of this is the VS-EPR general notation for any molecule or ion that has 20 valence electrons. So this really organizes a tremendous amount of information. This general formula down here, AX2E2, is the same for all of them, not just HOBR. So I don't have to memorize a shape for HOBR and then a different shape for some other 20 electron molecule or some other 20 electron molecule. I'm just going to put the 2 atoms in here, whatever they are, and then it's going to have 2 electrons, and I'll put the central atom, whatever it is, right there. Okay? The Lewis dot structure would look like this. We would have kind of guessed that by looking at the Lewis dot structure for oxygen. Oxygen has 2 lone pairs and 2 unpaired electrons. The unpaired electrons are the sites where covalent bonds form. So I would expect this without doing the math. In fact, if I'm going to do this one, hey, I'm just going to write that down and not even take the time to do the math because I know the Lewis dot structure for oxygen and that's going to be correct. Okay, and then I put valence electrons around lone pairs of electrons around the other atoms. This will give me a total of 8. Remember that pair of electrons is 2 electrons, so 2, 4, 6, 8. I've got an octet around the bromine. I've got 2, 4, 6, 8, an octet around oxygen. Hydrogen has 2 electrons. That's like helium for it. So we don't put lone pairs around the helium or the hydrogen, even though we included 7 up here when we did the math. The math is just helping us get the answer. What if I had FSO+? Well, this is an ion that, I don't know, maybe exists, maybe don't. We don't care. We've got 7 electrons from the fluorine. We've got 6 from the sulfur and 6 from the oxygen. Now, where did I get that? I looked them up on the periodic table. Fluorine is in group 7. Sulfur and oxygen are in group 6. So 12 and 7 would be 19, and I remove 1 to have 18. Okay, so because it's positively charged, I need to remove an electron. I've got 18 valence electrons in this molecule. Now, I've put them already up here in the order I wanted you to put them in when I wrote it down, FSO. But technically, since there's just 1 atom of each kind, either one of them could be the central atom. But we would have picked sulfur because it's the least electronegative. Fluorine is the most electronegative atom on the chart. Oxygen is second to it, and sulfur is below that. So sulfur belongs in the middle. If I do the math, I got 18 valence electrons. I divide by 2. I can make 2 octets. There'll be 2 electrons left over. That's going to be the M. So it's AX2. Now, that's got to come out to be the same as the number of atoms attached to the central atom. And there are 1, 2. If this doesn't work here, you've missed this. So if you calculate a 3 right here, and you look up here and you say, oh, that can't be true because I've only got 2 things, then you've made a mistake somewhere. So you can go back and fix that. Now, the remainder, I need to see how many pairs can be left on the central atom if there is a remainder of 2. Well, there's 1. So the VS-EPR notation is AX2E, and that's true for this ion, but it's true for any other molecule with 18 valence electrons. So again, we've organized a tremendous, you might have hundreds of molecules that could have 18 valence electrons, but they all have this VSEPR notation, and we're going to see that gives you the exact specific three-dimensional shape of the molecule. That's where we're going with this. So this is the structure, and then what do we say we do? Okay, you've got one lone pair. So I should put one lone pair on the sulfur first. That's just to make sure I don't screw that up. Then I put a bond to each of the other atoms. Now, I've got this structure now from the mathematics. Don't do what the book says. Book says put a lone pair here, put octets around here, check it and see if it's right. No, it won't be. It'll be wrong. If the math says there's one lone pair, there is exactly one lone pair on the central atom, no more. So to create an octet on the central atom, I need to add a double bond. Now, oxygen is, remember, oxygen had two lone pairs and two bonded positions, so it can have a double bond easily. Fluorine never does. Fluorine only has a -1 charge, and it only has a covalency of 1. Fluorine, like hydrogen, can never be in the middle of a molecule of any kind. No molecule of ion can have fluorine in the middle with two other things that are more attached to it. It's always going to be a peripheral atom. So if I had a very, very complex molecule and I had several fluorines to go on, I would never put them anywhere in a line with two atoms attached to them. They always have to be on the periphery, and hydrogen does as well. Okay, so now, how do I get the octet on the central atom? I need two more electrons. They have to be paired. They have to be bonded electrons, and they should go to the oxygen. Now you can put them to the fluorine. We can make it work. That would be a resonance structure. We talked about a while ago, if there's more than one way to do that, it's a resonance structure. But we would find out that this one, later on we'll study this in great detail, and especially in Gen Chem 2, and we'll be able to reject the structure with the double bond on fluorine easily. Okay, complete the octet on oxygen, 2, 4, I need two more pairs, 6, 8, and then complete the I didn't complete the octet on fluorine, did I? All right, pretend I've got a pair here, a pair here, and a pair here. Sometimes I take shortcuts. Okay, all right. Now, let's do carbonate. And notice what I said? I said carbonate. I didn't give you the formula. And from this day forward, we will begin doing things like that. So very common ions like carbonate, I sort of expect you to know its formula already. It's CO3 with a -2 charge. So I've got 4 carbons in group 4, 4 valence electrons. Oxygen's in group 6, I've got 3. 3 times 6 would be 18. I need to add 2 because the carbonate ion is -2 charged. So I add 2 more, plus the carbon gives me 24. So I've got 24 valence electrons in carbonate. Let's do the math. Okay, if I divide 8 into 24, I get a 3. The remainder is 0. Kind of trivial, but I want to do the math. 2 divide 0 by 2, I get 0. So this is just an AX3. It's got 3 bonds and no lone pairs. It's AX3. So again, not only does carbonate have this structure, every molecular ion that has 24 valence electrons has this shape as well. So this is really powerful. Now, here's what we had to do. Remember, we had no valence electrons. So I would have put a carbon here, an oxygen here, an oxygen here. I can't put any lone pairs on, so I have to put a double bond somewhere. Well, could I put it here? Yes. Then I could, if I had it there, then I would have 2, 4. I need 2 more pairs, 6, 8. I have 2 here, 4, 6, 8, and 2, 4, 6, 8. I have octets around all my peripheral atoms, and this is one possible structure. Remember, it is a -2 ion, so you really ought to show it as a charged species. It wouldn't be good to leave that charge off. Carbon trioxide can be made with great difficulty, but it wouldn't have this structure. Okay, all right, so I asked the question, could the double bond be here? Answer is yes. Could it be here? The answer is yes. And you would get this kind of structure. Again, the only difference is I've moved the lone pair here, and I've moved, well, I've essentially put a pair of electrons into here from out there, and I took that pair and put it out here to get this. And I've got that. And now, could it be over here? The answer is, of course, yes. And it could be in either one of these three positions with equal probability. Now, if I were to look at each one of these structures individually, I would say, well, there's a double bond. It's stronger and shorter than the carbon-oxygen single bond. So I would expect 2 long bonds and 1 short bond in this one, and 2 long bonds and 1 short bond in this one, 2 long bonds and 1 short bond in this one. But in reality, carbonate has 3 bonds that are equal in distance. So what we can imagine is that all 3 of these add together, and the real structure is 1/3 this structure, 1/3 this structure, and 1/3 this structure. So essentially, in the real molecule, that extra pair of electrons is distributed over all 3 atoms. Now, I want to remind you of Pearson's law of stuff. Stuff goes from where it is to where it's not. Or as we say in Kentucky, stuff goes from where it is to where it ain't. Okay? So whenever we have electron stuff, if it can spread out to other places, that makes the structure more stable. So this resonance that we have here causes carbonate to be a very, very stable ion. And it happens because by having this resonance, I can take this localized high concentration of electron charge, 4 electrons, and I distribute all of them equally around the whole molecule. So it's got essentially 4 bonds distributed in 3 places. So effectively, it's a 1 and 1/3 bond for each one. And so that gives them all exactly the same size, and it stabilizes the structure. When you get to organic chemistry, remember resonance, because resonance is extremely important for organic compounds. Okay, so you got 3 resonance structures in this. Each one contributes equally. The real structure of carbonate is, it's a flat molecule or ion, just like a pancake. All 4 of these atoms are in the plane. They're flat. All 3 of the angles are equal. They're 120 degrees. And this is a very symmetrical, stable structure that you get for carbonate. Now, here's a non-central type. And how do you handle the shape of a non-central type molecule? Well, we have to go back, and what I like to think about is I call it my Tinker Toy model. I'm going to take little Tinker Toys that have places for things to bond to them, and I'm going to put molecules together with them. There's 2 carbons. Carbon typically forms 4 equivalent bonds, 4 bonds to every carbon. Now, you can have 4 single bonds. You could have a double bond and 2 single bonds. You could have 2 double bonds. That would be 4 bonds. Or you could have a single bond and a triple bond. That would be 4 bonds. So carbon can bond either single bonds to other things. It can bond through double bonds to other things. It can bond through triple bonds to other things. Um, and it can form probably a countless number of molecules and have actually made literally hundreds of thousands that's been characterized. Hydrogen now can only have one bond and no lone pairs. So the hydrogen is going to be attached to the other atoms, but they can't be in line with the other atoms. I have to put all the other atoms together and then look at the edges, and I can attach hydrogens around the edges. Now, oxygen has two lone pairs and two bonds. It could be two single bonds, and if it did, that could put oxygen in line with some other atoms. Or it could have a double bond, and if it did that, it would have to be on the outside, on the periphery, to do that, if it had double bonds to it. So it can have two bonds and two lone pairs on oxygen, and they could be two single bonds or a double bond and two lone pairs. Okay, so these two atoms in this particular group could be possible middle atoms with the other things attached to them. So this is one of the structures you could draw. This carbon attached to this carbon, attached to this oxygen, and that oxygen attached to that hydrogen. Now, look at my Tinker toys and see if they work. 4 bonds on that carbon. That carbon's in good shape. 1 bond to each hydrogen. The hydrogens are all just 1 bond. This carbon's got 4 bonds attached to it. This oxygen has 2 bonds and 2 lone pairs. So I can put one of the carbons in the middle and I get this molecule. It's a very, very well-known, notorious molecule. It's called ethanol, and it's grain alcohol. I say it's notorious because this molecule you're looking at on your screen kills more people than any other accidental poisoning. Drugs are getting close now, but this is a drug too. It's alcohol. So, but this one results in more accidental poisonings. The reason for that is you can drink alcohol, and when you eat food, if you've had biology, you know there's a thing in the cell called the Krebs cycle, and what the Krebs cycle does is it takes the carbon sources from your food and it clips them off 2 carbons at a time. And it clips off 2 carbons at a time and puts them together, and it oxidizes them and makes ATP, or it stores them in fat or other molecules. It's interesting that every fat molecule in your body, every single one of them, has an even number of carbon atoms. And the reason for that is the Krebs cycle clips them off 2 at a time. If you don't need the energy, then it will just store it as fat and keep it for later use when it can metabolize the fat in the same way. But the fats are already organized to work well in the Krebs cycle because it has an even number of carbon atoms in it. So alcohol is just 2 atoms to start out with. If you've got alcohol in your bloodstream, it gets into your cells, it's going to be metabolized immediately. And you know, when you talk about the beer belly, it's not the beer belly. The beer got metabolized. Once the beer got metabolized, you didn't need the food, so the food got stored. So the beer belly is really a food belly. But now, the reason why this is toxic is in the Krebs cycle, when it clips off the 2 carbon atoms, it makes a unit called an acetyl unit. And that unit is then converted to ATP by oxidation, or it's stored to make fat. Now, if you overload, you're going to have this running in your system. It's going to cause the mental function change that occurs in alcohol intoxication. But if you overload the Krebs cycle, Then this goes to the liver. Your liver is an organ that looks for uh, impurities in your blood and oxidizes them and takes them out. Now, it oxidizes them through a process called free radical oxidation. And what that does is it can produce cancer, and it can also damage itself. Those free radicals that are used to kill the alcohol will kill liver cells as well. So if I had a good friend at Western, I'm saddened just to think about it. For years, he was a English literature professor, and I think kind of idolized the life of Hemingway, maybe. And so he walked around all day with a cup of what I thought was ice water. And we would meet at our faculty house and have coffee together almost every day. We were good friends, and we'd joke and talk with each other. I never knew that actually what he had in his cup was ice with vodka. He never got uh, intoxicated enough that anybody would notice it. But his liver was destroyed. And within probably a month or two of when he started showing liver failure symptoms, he was dead. So the guy who keeps the low buzz for a long time, those are the ones that are in danger. The guy that wakes up in a cornfield somewhere 2 days later and don't know how he got there, they usually just do that every so often and give their body a chance to recover. But if you wake up in the cornfield every morning, you've got a real problem. Okay. All right. Now, so this is one of the molecules you can make that has this formula, C2H6O. Here's another one. You can put the oxygen in the middle. So remember, we had two choices. One, we put carbon in the middle. The other one, we put oxygen in the middle. And again, we've got 4 bonds to every carbon, 1 bond to every hydrogen. The oxygen has 2 pairs and two bonds in it. But this is an entirely different molecule. This one is called dimethyl ether. And it was one of the first anesthetics that we discovered. It will put you to sleep. So when you get an excess of alcohol in your bloodstream, you get intoxication. When you get the excess of dimethyl ether in your bloodstream, it will put you to sleep. Anesthesia is controlled poisoning. If you regulate how much of this you put in, you can put the person in deep enough sleep, you can cut on them and they don't feel the pain. But if you continue that, if you put too much in there of any anesthetic, it'll kill you. So when you go in for surgery, you be good friends with the anesthesiologist and tell them how important they are to you. They're holding your life in their hand. And they've got to monitor you carefully to see that the poison they give you puts you to sleep but doesn't kill you. Now this one, we stopped using it a long time ago, because when you get put to sleep with dimethyl ether, you'll wake up, you lose yesterday's breakfast. I mean, it makes everybody violently sick when they wake up. So this is not a good anesthesia. And we've got some good stuff now that usually when I've been under a couple of times for some knee surgeries and things like that. They tell me to count back from 100. I'm probably make 96 and I'm gone. And then I wake up wide awake and I'm ready to go. It takes me a very short recovery time, usually, if I could put out. But these two molecules are quite different. Now, they're not resonance structures of each other. These are what we call isomers, isomers, isomers. And they are different three-dimensional arrangements. Both of these molecules have the same empirical formula. They would have the same percent composition, but one of them is in a three-dimensional shape that's different from the other one. And so they have different ways the atoms are attached in three-dimensional space, and those are isomers of each other. The molecule you call octane in your gasoline, the real octane molecule has 18 different isomers. That has the formula C8H18. There are 18 different molecules that have that structure, 18 different isomers. So they're very common. Okay, here's some checkpoints on it. Write the VSEPR notation of nitrite ion. Okay, I didn't give you the formula. Draw the Lewis structure of the nitrite ion. There are two resonance structures, and draw the Lewis structure for this one. So I'm going to switch over to my camera, and let's see, I'll need to give you this one, and I need to get this so I can see it. So let's start working. We have nitrite ion, NO2 minus. Now, if it had said nitrate, it would be NO3 minus, but nitrite is NO2 minus. Now, I want to do the VSEPR notation for it. So nitrogen, I'm not pulling out my periodic table. You should have one with you all the time so that you can refer to it. I've done this so many times over the last 50 years that I've got some of those things memorized. So nitrogen's in group 5. I, by the way, didn't sit down and memorize all of them, but it just happens after you use it a lot. There's 2 oxygens, and oxygen is in group 6. 2 times 6 is 12, and 5 would be 17. I have to add 1 more because of the charge. So that gives me 18 valence electrons. Now, you think ahead with me. What am I going to do with that? I'm going to take the 18, and I'm going to divide it by 8. And that'll go 2 times. And 2 times 8 is 16. And 2 remainder. And if I take the 2 and divide by 2, I get a 1. So my VSEPR notation is going to be AX2 E1. And sometimes we don't put the 1 in there. We might just say AX2E. But I put the 1 in here just to emphasize where it came from. So remember, what you get here is what goes there, and what you get here is what goes there. So that's going to be the VSEPR notation for it. Now let's do the Lewis dot structure. I've got 3 things attached. So it's going to look like this. I'm going to put the nitrogen in the middle. I'm going to look at this. It says I have 1 lone pair. So one of these positions is a lone pair. It wouldn't matter which one. Oxygen is on the other 2 positions. Now I've got 2, 4, 6 electrons. I need 8. I can't put a lone pair. Don't do that. I'm going to put a double bond to one of these. Could I put it here or here? Answer is yes, either one. If I put it here, that's going to need 2 more lone pairs on this central atom. If I have the double bond here and a single bond here, I'm going to need 3 lone pairs on this atom. And then, of course, there's a resonance structure. Sometimes we draw resonance structures separated by a double-headed arrow like that. And again, same basic shape, except the double bond is going to go over here, and the single bond over here, the nitrogen here, the lone pair here, 2 pairs on this one, and 3 pairs on this one. So, and now each one of these is a -1 ion. And so I'd really need to show a -1 charge for everything. So that's the structure. There's 2 resonance structures for it. And that gives us the VSEPR notation and the shape. Any of you have any questions about that? Okay, let's look at the other problem on this one. We have C3H6O. And now this cannot be a math problem. You cannot have a central atom in this. You could say, oh, okay, I could put oxygen in there and put 3 carbons and 6 hydrogens on the oxygen. No, you can't. You can't have more than 8 electrons around oxygen. Oxygen is in group 1. Now, some of the other atoms, the sulfur and the others below, they can have more than 8 electrons around the outside. But oxygen and no element in the first row can have more than 8 electrons around it. So you can't draw a central atom for this molecule. Now, we've got to make some isomers. So I'm just going to do some stuff. I'm going to put all of the carbons together. And then I'm going to put the oxygen. Why didn't I put I could put a hydrogen there, but I can't put anything on the other side, can I? No. Okay, so let's go with that. Now I've got 6 hydrogens to go in. Let's see, if I put 3 of them here, and I'm going to need 1 of them here. Well, maybe not. Let's go and just do it this way. I got 1, 2, 3, 4, 5, 6. Let's see if I can get a structure to work there. So I put hydrogens on each one of these. Now, I've got carbon. All these carbons this far have 4 bonds. They're good. This one's not. All of the hydrogens have 1 bond. This one needs another bond. I can put it right there. And if I put it right there, I'd need 2 pairs on oxygen to complete the octet. Now, oxygen's right. That carbon's right. That carbon's right. That's carbon's right. That's one of the isomers that I could draw. Okay, let's try to build on that one a little bit and see what we can get. Let's suppose I put the oxygen here and put a hydrogen over here. Is there a way to make a structure? Then I need 3 of the carbons here, hydrogens here. I need 2, maybe 2 of them there. I don't think that's going to work because this one's going to be messed up. Let's try this. And now I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yes, look at that. Now, so I think with this CCCO, I can't think of another isomer like that. I need a 2 pairs on the oxygen, remember, to make 2 bonds and 2 lone pairs. 1 bond, 4 bonds, 4 bonds, 4 bonds. And for this hydrogen up here, 1 bond as well. Well, let's put the oxygen in between 2 of the carbon, the 3 carbons. Can I put it in here and generate one like that? Well, let's see. I can put a hydrogen here, a hydrogen here. Of course, I got to bind all of these things together. Hydrogen here. I would need another hydrogen here, another hydrogen here, and the lone pair here, and I would need 3 more hydrogens here. That's not going to work, is it? I've only got 6 hydrogens, and I'm going to need 1, 2, 3, 4, 5, 6, 7, 8. So that's not going to work like that. Okay, let's try something else. Let's, instead of putting 2 hydrogens on here, let's make a double bond there. Now let's see, does that work? 1, 2, 3, 4, 5, 6, 7. No, that didn't work either. Let's do this. Let's put a triple bond here and see if I can make it work. Now I've got 4 carbons, 4 bonds on that carbon. 1, I've got, oops, I can't put 1 there. And let's try this one and see if that worked. So 1, 2, 3, 4. Whoops, you know, I don't see a good structure like that with oxygen in the middle. Okay, let's see if I can put oxygen as a peripheral atom. Let's do it like this. And let's put the oxygen down here with a double bond like that. Now, will that work? Okay, 4 bonds, 4 bonds, 4 bonds, 1 bond to each hydrogen, and 2 bonds to the oxygen. I need 2 lone pairs on the oxygen. Hey, look at there. We got another one. That's at least 3 of them. And that would satisfy the problem. You can come up with some more of them. Let's see. Now, you said, well, okay, why don't we put the double bond over here to the oxygen? Well, you see, that would be the same as this molecule up here, just turned around. So you can't do that. So I can't get it like that. There's probably lots of other ways. We haven't talked about it, but what if I did this? Put the 3 carbon atoms together like that. Now, can I make, oopsie daisy. Yeah, I wanted a triangle. Well, let's do it, doggone it. Put an oxygen right here. Can I make that work? Hey, look, I think I can. If I make a little square, 3 of the carbon atoms in the square, an oxygen joining the 2 ends. Now I've got 1, 2. Put hydrogens here and here and here and here and here and here. Okay. Hey, that did work, didn't it? Okay. So I can have a structure like that. That would be 1 more. Let's see, there's probably 1 more ring structure perhaps that I could draw. Can I put all just the 3 carbons together like that and put a double bond here, and then nope, that's not going to work, you see, because I've only got 4 carbon atoms. So there's still 1 more structure. I'm not sure which one it is because I can't. Oh yes, there's another one right here. The other one that I messed up there is, again, 3 carbons in a row, an oxygen like this. This is the other one. And then I need 2 hydrogens here, 1 more here, and 2 here. 1, 2, 3, 4, 5, 6. Yes, that's it. That's the 5th one. Okay, so now you saw how I did. Of course, for me, the hardest one was this one, of course, trying to draw that non-octet rule type. Well, it's an octet rule molecule. Everything has 8 or 2 around the hydrogen, but the non-mathematical. I can't use VSEPR notation on that whole molecule. Now, once I've got it formed, I'm going to show you something that you can figure out the shape. Now, when we got 3 things, when I've got 2 things attached to something, it's going to be in a straight line because that will be the minimum repulsions between the bonded pair of electrons here and the other bonded pair here. If I've got 3 things attached to my central atom, then that's going to give me a trigonal planar, a planar structure like this, and the bond angles are going to be 120. This bond angle is going to be 180. When I have 4 things attached, it's a 3-dimensional structure. 4 things attached is called a tetrahedron, and it has bond angles of 109 plus, about 109.5 degrees. Now, and these are all perhaps octet rule structures. If the central atom has more than an octet, it could have 5 things attached. I'll go into more detail about this later. But it's what's called a trigonal bipyramid. These four atoms here are in a plane. Think about a globe. This would be the North Pole. This would be the South Pole. This would be the equator. So it's got 3 points in this equatorial group and 2 bonds in this axial group. There are 2 sets of angles. The angle from this one down to the equatorial plane is always 90 degrees everywhere. And the angle between these two is 120 degrees. You can think of this, and should think of this, as this combined with this. There's 2 unique different parts of the trigonal bipyramid, a linear part and an equatorial trigonal planar part. Then the octahedral is the only other shape that we'll look at. And this is just XYZ coordinate system. So it's a 3-dimensional coordinate system. All your angles are 90 degrees. And again, if I'm thinking of the octahedron, I think of it as 3 of these, 3 linear pieces, one along the x-axis, one along the y-axis, one along the z-axis. So now, having said that, let's look at, if I were building the shape of this molecule, what would it actually look like in 3 dimensions? Well, if I put my finger right there on this first carbon atom and say, what would be the VSEPR notation of that carbon atom? It would be AX3. So it's 3 things attached. So these angles, I've drawn them approximately correct, 120 degrees. So that angle's 120, that's 120, and that's 120. Now, what if I looked at this one? What's it? It's got, okay. It's got 3 atoms attached and no lone pairs. It's AX3 also. So this structure is not the way I've got it drawn here. In fact, it's a trigonal planar structure. So this one would be, and I should make these 120. I could make this part going off up like that, and this hydrogen coming off here, giving me the 120 angle that I didn't have a while ago. What if I'm looking at this carbon atom? What's it got attached to it? 1, 2, 3, 4 things attached. It's AX4. That's 109 degrees. So the angle around that carbon atom is 109 degrees. What about this guy here? Well, it's got 1, 2, 3, 4 things attached to it also. Remember when I said things, it's pairs of electrons. Doesn't matter whether they're bonded or non-bonded. It's got the same number of pairs. So it's 1, 2, 3, 4. So it's 109 degree angles as well. Okay. All right. Okay. All right. I think I need to back up a bit. I bumped my, yeah, this is where we were. So here are the, this would be the workout of this checkpoint. Okay, let's escape out of that, and I need to go back to screen share. And okay, I think this would be a good place for us to take a little break. It's a little after, maybe 11 or 12 minutes after 9 now. Let's take about a 10 or so minute break. Let's say, let's do a 9:15. That's not quite 10. Okay, so let's take a little bit of break here. I'll pause the recording, and yeah, okay, let's take a look at the practice exam. Okay, and let's see if I can make it bigger for you guys to see. Okay, that should be big enough. And now I need to expand the screen just a little bit. That should be okay. All right. Let's, if there's a problem on here that you don't really need me to help you with, then we'll skip it. But I'm guessing the first one is one you might want me to do. What's the wavelength of channel 5 on TV is 3.88 meters. I thought that was an interesting one. You think about the channel you're watching on TV and compare that to the size of your TV. The wavelength is probably bigger than most people's televisions. A lot of people have some big screen TVs, but I think this one is a little bit bigger than that. If I run the TV on my media room projector, it's maybe about that size. Okay, but anyhow, what's the frequency of the radiation in megacycles per second? So the relationship that we need, and I need to, I keep forgetting, I've got to change the camera before I want to go to, no, I don't want to stop it. I just want to go to the HD cam. There we go. All right, and now go back to, no, I don't want to do screen share. Okay, here we go. So the relationship between wavelength and frequency is the wavelength lambda times the frequency nu is equal to the speed of light c. So the frequency is going to be c divided by the wavelength, and the speed of light is 3, that's given in the problem, times 10 to the 8th, and I've given that in 3 significant figures. You will have these constants on your exam the same way as this. The wavelength is 3.88 meters. Okay, well, we're good here. Often we talked about light where we had it in nanometers, but this is given in meters. And now the speed of light was this many meters per second for one photon. So if I divide this out, I'm going to get the frequency. The meters are going to cancel, and it'll give me seconds minus 1, or per cycles, waves per second is what that would actually be. So if I take my numbers, 3 with an exponent of 8 divided by 3.88. Yes, that gives me 7 point, we get 7.7319, whole bunch of digits. And our power of 10 is 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. Okay, and now what is this? This is cycles or waves per second. And I'm looking over there, I don't have that. I have megacycles per second. So I want to convert from cycles, I'll just abbreviate CYC, to mega cycles. Mega is 10 to the 6th. So I want to divide that answer that I've got on my screen, divide by 1 with an exponent of 6. And what I come out with is 77.319, so 77.3 megacycles per second. So that gives me my units. Okay? So that one's just plugging into this formula. So when I'm looking at this problem, I saw wavelength and frequency. That should have keyed me to remember this formula. And then from that point on, It's just plugging in what I know and solving for what I can. For the second one, how much energy would be received when 3.5 moles of light with a wavelength of 650 nanometers is absorbed? So I've got energy and wavelength. What's the relationship? The energy is equal to h, Planck's constant, times c divided by wavelength. So this clues to this formula. So let's put in the numbers. I've got the wavelength and I've got the constant, so let's put it in and see what we get. We get 6.626 times 10 negative 34. I'm not going to copy units, it's joules seconds. I'm just going to be sure I got SI units every time. This is 3 times 10 to the 8th. It's actually 3.00, 3 significant figures, but right now we're not worried about that. We'll round off at the end. The wavelength is 650 nanometers is 10 to the minus 9 meters. Now, distance has to be in meters. I can't put nanometers here. I have to put 650. Nano is 10 to the 9th. 10 to the minus 9, not 10 to the 9th. Okay, and this is 10 to the negative 34. My negative sign didn't come out real good. Okay, so let's do our math. We've got 6.626 with an exponent of negative 34 times 3 with an exponent of 8 divided by 650 with an exponent of minus 9. So here I came out with a number. I've got a number. It's 3.058 and a whole bunch of other digits times 10 to the minus 19. And now what is that? That's going to be joules for one photon. So it's joules per photon. The answer is just in kilojoules. So I need to calculate for the number of photons that's shown in this particular problem. Okay, how many photons? We've got 3.2 moles. 3.2 moles. And each mole is 6.02 times 10 23rd, plan ahead, photons. So I've got to multiply my answer times 3.2 times 6.02 times 10 to the 23rd. So I got my answer on here, times 3.2 times 6.02 with an exponent of 23. Let's see, 3.2, yes, times 6.02 times 10 to the 23rd. So I'm coming out with the energy is going to be 5.89122 and some decimal places. And now what is this in joule? It's just in joules, see? Joules per photon, it canceled out moles and photons. So this is in joules. I'd look at the answer and say, no, the answer is in kilojoules. So I have to convert. So I want to put joules down here. I want to put kilojoules up here. And kilo is 10 to the 3rd, so I'll put a 10 to the 3rd down here. Now I'm going to have kilojoules if I divide this number by 1,000. 10 to the 3rd. So I come out with an energy of 589.122 and some more digits, kilojoules, and to 3 significant figures that we had back up here with the speed of light. That's going to give us then the energy, and that's response D on the exam. All right. Number 3. Um, okay. So for number 3, we've got what mass, what is the mass in grams of so many moles of light? So when I see that, the mass for light. Okay, now that should give us the Broglie relationship. The relationship is lambda is equal to h over m c if we're talking about light. Now it could be, if it's a particle, then I would put the speed of the particle, not the speed of light, in here. So we want to solve for the mass. So the mass is going to be h over lambda times c.
Could you
So
switch back to the screen you're working on?
this is number 3.
Yeah, I just can't see your work. It's too
Oh,
small.
oh yes, yes. Thank you.
Yeah,
Uh,
of course.
I've got to stop sharing every time before I can show you what I'm doing. Okay. All right. Now, so this is the relationship that we need, and I can plug in the numbers. Planck's constant, 6.626 times 10 negative 34, and that's in SI units, is joule seconds. The wavelength that I have is 550 nanometers, so it's 550 times 10 minus 9 meters, and the speed of light is 3 times 10 to the 8th. This is all multiplication and division. We've got 3 significant figures here. Okay, so now I can do my math. I can find my calculator right here. So 6.626 with an exponent of negative 34 divided by 550 with an exponent of minus 9 and divide by 3 with an exponent of 8. So I've got 6.626. Well, you can't see it either. Yeah. Yeah, maybe you could there. Got too many reflections. Okay. All right. But anyhow, it looks like I entered the correct numbers. Okay, so what I'm coming out with is the mass is 4.0157, a whole bunch of digits, times 10 to the minus 36. Now, what is my unit here? Mass, kilograms. It's kilograms. For how much? 1 photon. You see, anytime I'm putting a wavelength in, that's the wavelength of 1 photon. So this is the energy for 1 photon in kilojoules. Well, if I'm looking at the answers, my answers are in grams and not grams per photon. I can get the grams all right just by changing that number right there to 10 to the third. Now I've got grams, but I got to get rid of photons. How many photons do I have? Well, I have 3.12 moles, and each mole is Avogadro's number, 6.02 times 10^23. And then photons and moles would cancel, and I would wind up taking my answer times 3.12 times 6.02 with an exponent of 23. Now, you notice when I did this problem, I wrote it down for you to see, but I never took any numbers off my calculator. I did all the calculations inside the calculator, and that saves me time. of writing it down if I'm taking a test, and that saves me my nemesis of transposing digits. Okay, so what I'm coming out with is a mass is 7.54 times 10 to the minus 12 grams. So that should be, wait, did I do that? Oh, I forgot to multiply by my 1,000 up here. Oh, and look what that did. That would have made me get the wrong answer. Times 1,000. Okay, all right. Now I got the right answer. I didn't multiply by 1,000. When I multiply by 1,000, that is 10 to the minus 9. Now I've got the right answer on the problem. Have to be a little careful about things like that. Okay. All right, let's see what we got for now for number 4. Let's see, I have to share screen so you can see that. Okay. Number 4. What's the velocity required for a neutron to have a wavelength equal to 100 times the diameter of the neutron? Okay. Well, now when I'm talking about mass or wavelength of particles, that means a de Broglie relationship for particles. Lambda is equal to h over m times v, the velocity of the particle. So I need to solve for velocity.
I'm sorry, can you switch back to the,
Yes, you need to see what I'm doing.
yes, I'm sorry.
No, thank you for doing that. Okay. And so, no, I don't want to screen share it. You're seeing my pad now. That's okay. Okay. All right. Velocity is equal to h over m times lambda. And now let's see what we got given in the problem. And I can plug my numbers in. And I know the mass of the neutron. It says the mass is 1.67 times 10 to the minus 27, and it's in kilograms. So that's okay. Mass is supposed to be in kilograms. Now, if that had been given the mass in grams, and that's probably what you would find in the back of your book if you looked up the mass of a neutron. Probably would be in grams, I'm guessing. Might not be, I don't know. I know Planck's constant. I want the wavelength to be 100 times the diameter of the neutron. Well, the diameter is given in the problem. So I want 100 times the diameter of the neutron is 1.1 times 10 to the minus 15 meters. That's in the correct unit. So all I got to do is plug these numbers in, and that should give us the velocity. Okay, so Planck's constant is 6.626 with an exponent of negative 34. I want to divide that by 1.67 with an exponent of minus 27. I want to divide it by 100 and divide it by 1.1 exponent minus 15. So let's take a look and see. 6.626 times 10 negative 34 divided by 1.67 times 10 to the negative 27. Oops, I see a mistake. I divided by 100. I should have divided. No, I did. It was 100. Okay, 100 and divide by 1.1 times 10 negative 15. It looks like I got it set up correctly. So velocity I'm coming out to be 3.6069 bunch of digits times 10. And let's see, my power is 1, 2, 3, 4, 5, 6 10 to the 6. So, so it should be 3.61 times 10 to the 6. Yeah, it's 3.61 times 10 to the 6. And what's my unit? It's MKS. It's meters per second. And if I look at the answer, that's the units given in the answer. So that should be the correct answer. And it's C. It is correct. Okay, now. Yes.
Going over, I kind of got lost when you did the 100 divided by that number for the wavelength. Do you mind explaining?
Okay, yes. I'll write it back down here. My numbers were 6.626 times 10 negative 34. And I want to divide that by the mass is 1.67 times 10 minus 27. And I want to divide that by the wavelength. The wavelength is 100 times 1.10 times 10 to the minus 15. Like that. Now, when you're doing a division, you can do grouping symbols like I've got there and do all that kind of stuff, but you'll save yourself keystrokes and time if you just enter this number and divide by this number and divide by this number and divide by this number. You want to divide by everything that's in the denominator. And that's crucial because a lot of times people say 6.626 times 10 negative 34 divided by 1.67 times 10 negative 27 times 100 times 1.1 times 10 to the negative 15. That'll be wrong every single time. So you don't want to do that. You want to divide by everything in the denominator or put grouping symbols in, and then you can do that. You know, if I put my grouping symbols in, I could make it work with times, but I'm not going to do that just to get it right, because I can get it right this way without having to put the grouping symbols in either. So it still saves me time. Okay? That makes sense now?
Yes, thank you.
Yeah, good. Okay, all righty. Let's see, what are you seeing? You're seeing my pad, and you need to see my other screen. Okay, let's do number 5. Now, this one is how many atoms in an atom could possibly have n equal to 3? Well, let's think about it. If n is equal to 3, then you can have various kinds of values for, I said 3. Okay, if n is equal to 3, what are the possible values of L? L can be equal to 0, or L can be equal to 1, or L can be equal to 2.
Can you switch back, please? I'm so sorry.
You'd think I'd learn after a while, wouldn't you? Okay, all right. Thank you for reminding me. I'll get it right maybe before we're done. Okay. When n is 3, L can be 0. That would be 3s. When n is 3 and L is 1, that would be the 3p orbitals. When n is 3, L can be 2, that would be 3d orbitals. Okay? Now, there are multiple values of m for each one of these. So when m here can only be equal to 0. If L is 0, m is 0. But in the 3p orbital, there's an L equal to m equal plus 1, 0, and minus 1. D orbitals, L is 2, so I go from plus 2 to plus 1 to 0 to minus 1 and minus 2. Now, when I'm putting electrons in, they have the spin. Spin is either plus or minus 1/2. So I can have a spin up or spin down for that one. I can have a spin up or spin down for that one. A spin up and a spin down for that one. up and down, up and down, dot, 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 up and down. Well, how many electrons total would that be? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18. That would be 18 electrons could have n equal to 3. And that's response D. Now, here's the quick and dirty. It's 2n squared. So you don't have to draw all this stuff out. I could just say 2 times 3 squared. 3 squared is 9 times 2 is equal to 18. So I can use this relationship to get the number of electrons with n equal to 3. Now you have to be careful of the wording, okay? If it's the number of electrons with n equal to some number, then you can do 2n squared. I could ask you how many orbitals, that would be different. I could ask you how many different shapes of molecules could have n equal to 3, and that would be a different number. So you want to be sure that you're only using this formula for this kind of problem. Okay, that's quicker than working them by hand. Okay, and moving right along. And now I do have to share the screen.
Dr. Pearson,
Yes.
I had a question about the previous one. Wouldn't it be easier to just go down to the third level and look at argon that has 18?
That's dangerous. It is correct. That is true. But okay, I guess it would still work for all of them, wouldn't it? If you said n is equal to 2, you'd be 2s2p, you'd be neon, and that would be 2 times 2 squared would be 4, that would be 8. Okay. I guess that would work. Yeah, that would work. If it's a noble gas, and it would be if you had those all
Right.
4, I guess. Yeah. Okay. Yeah, that would work. But that little formula works also. You wouldn't need the periodic chart for that, but that's good. Good to notice that. Okay, now I need to do a screen share with you. Get back over here. And now we are doing number 6. And number 6 says how many electrons can have n equal to 3 and L equal to 2. Okay.
It said elements. Was it supposed to be electrons?
I'm sorry?
It said in the question how many elements, not electrons. I didn't know.
Yes. How many different elements? Yes.
Sorry.
Okay, you're right. So n equal to 3 and L is equal to 2. So n is 3 and L is 2. That's a 3D orbital. Okay, how many electrons could be in a d orbital? Okay, we go 1, 2, 3, 4, 5. From +2, +1, 0, -1, -2. Now these are the m values for the 3D orbital. Now, it said how many electrons. So if I go 1, 2, 3, 4, 5, why'd I put them in like that? 6, 7, 8, 9, 10. Because that's the way they fell. You put in 1 electron in this one, then the second one goes here, the third one here, the fourth one here, fifth one here, 6, 7, 8, 9, 10. So altogether there are 10. And that's going to be response A on that question. We go back and share. Back. Okay. What are the values of the 4 quantum numbers for the last electron added in a P4 configuration? Okay. And this is number 7. And I've got a 4 P4. Okay, it's a p orbital, and p orbitals, the 4p orbital, L is equal to 1, so I go from +1 to 0 to -1. And I'm going to put 4 electrons in. There's 1, there's 2, there's 3, there's 4. Now that's the last one that was added. And it says the value of 4 quantum numbers for the last one in a 4p4 configuration. Well, n is going to be equal to 4. L is going to be equal to 1. M for this electron is +1. And spin for this electron, or m sub s, is -1/2. So we've got 4, 1, +1, -1/2. And by the way, when you're doing m, it has a sign to it. So don't leave off the sign even if it's +1. It should be listed. So 4, 1, +1, -1/2 is going to be the quantum numbers for that particular electron. And I need to screen share to get back to here. Number 8. Okay, well, this is the one I warned you about shows up, so I made it show up here. We want to do chromium. And let's grab a periodic table. I need to print one out. That's a little more convenient than using the textbook. But now here's chromium, and I need to stop the share so you can see my periodic table. So it should be, there's the periodic table. Now we're doing chromium. That's it right there. Now chromium, if I want its electron configuration, I go up to the end row above it. It's argon. So chromium has an argon core. Okay, now where do I go after 18? I'm going across to chromium. This is this way. This is the 4th row. So when I get to calcium, it's 4s2. That's what I'm expecting. And now how many in this row? The first row of the d orbitals is the 3d. This row of d orbitals is going to be one less than that for n. So if this one's 4, that's 3. If this one's 5, that's 4. 6 and 5, 7 and 6, and so forth. Now chromium, I go 1, 2, 3, 4. I go, oops, should be 3d4, but it's not. This is the one, the exception. The exception is one of these electrons goes over to here. So chromium orbital designation is going to be an argon core. The 4s orbital is going to have 1 in it. Then I'm going to have the 3d plus 2, 3d plus 1, 3d 0, 3d minus 1, and 3d minus 2. Each is going to have 1 electron in it. Okay, so it's going to have a total of 6 unpaired electrons. So if I go back to screen share to pick our answer, here we are. The s orbital has 1 electron in it. The 3d0 has 1 electron in it. And the 3d minus 2 has 1 electron in it. So the correct answer for this one is D. Okay. Let's see what we're looking at next. Number 9, okay? And 9 is, we're looking for the ground electronic state of the vanadium plus 3 ion. Okay, let's go over here. And we want vanadium plus 3. Well, See, what we first have to do is we have to do vanadium. For positive ions, we have to do the neutral first. Well, vanadium is this element here. So it's going to be argon 4s2 3d3. I'm just going to leave it like that for the moment. So it's argon 4s2. Argon is 4s2 3d3 would be its orbital designation. Now, I'm forming, remember what this atom looks like. I've got a little core down here that's argon. Next, I've got the 3d orbital with 3 in it. And further out, I've got the 4s orbital with 2. So when this other atom comes in to react with the vanadium atom, what's going to happen is it's going to pull out these 2 electrons first, and that would make vanadium plus 2. I want vanadium plus 3, so it's going to get one of these. So it's going to be the argon core, and the 3d, 4s is gone. The 3d is going to have 2, so one of them will be in the plus 2 orbital, and one of them will be in the 3d plus 1 orbital. So the orbital designation of the ion, you do the neutral first and peel off electrons from outside in. And generally the s and p orbitals are the one that's on the outside. In this case, only s orbitals are on the outside. We get 2 of those and 1 of the others to give us the electron configuration. And let's go back and screen share. And that would be this answer, C. I'm going to determine the symbol for an element from its quantum numbers for its last electron. Let's take a look at that. So for number 10, we've got N is equal to 4, L is equal to 1, M is equal to 0, and S is equal to minus 1/2. Okay? Now, let's do this the quickest way possible. Okay, N is 4. I'm going across this row. When L is 1, that's P. So that means I'm going all across to here. Now, M is 0 and spin is minus 1/2. This is what's critical. It's minus 1/2, which means I'm going to go across the P orbitals a second time. So I'm looking at the 4p orbital, this row right here. It's one of those elements. And I'm going to put spin minus 1/2, and I'm going to stop right here. So I'm going to go 1, 2, 3, 4, 5. And this is plus 1, 0, and minus 1. And so it's this electron was the last one we put in. We put in 1 up, 1 up, 1 up, 1 down, and 1 down. This is the last one, and it's 1, 2, 3, 4, 5, the 5th element in the 4p row. So 4p is this row. So 1, 2, 3, 4, 5. This one is bromine. That would be bromine. Now, just a quick thing. If I'm going across this p orbital, this one is plus 1, 0, minus 1 for M. And this one's plus 1, 0, minus 1 for M. The first 3 across, it's plus 1/2 for the spin. The last 3 is minus 1/2 for the spin. So if I had noticed it's minus 1/2, I would say, okay, plus 1, 0, minus 1, plus 1, 0. It would be this one right here with a minus 1/2 spin. So that would give me the 4p5, which gave me the symbol for the element. So that's how you use the periodic table to identify an element from its 4 quantum numbers.
Dr. Pearson,
Yes.
a really quick question just to clarify. When it comes to like transition metals, I was kind of confused. So if N for the if it's talking about a transition metal and it's like N equals 5 or let's say 4, I think that was on the quiz, would it be the second row down for the transition metals?
If N is 4, here's, you still got my, say if N is 4, it's going to be going across this row here. When I go across from element 19 all the way over to 30, is that 36? Yes, 36. I'm going across this row. So if N is 4, this row is 3D. Now, if N is 4 and you're in the d orbital, it's this row.
Okay, so if L was like 2.
Yeah,
would,
see, this row would be the 5th row, but the d orbitals would be the 4th row. So it's kind of best to remember this first, well, go back up here. 1, 1s, 1s1, 1s2. Row 2, 2s and 2p. There's no 1p. You can't have a 1p set of orbitals. 2p is the first place you can have orbitals. Then we go 3s, 3p, but we can't have a 2d either. So we have to go down to here, 4s, and then this will be 3d. So it's always going to be 1 less than this number. So the first row of p orbitals is 2. The first row of d orbitals is 3. The first row of f orbitals is 4. So this would be the 4f. So 3d, 4d, 5d, 6d, 4f, 5f, 2p, 3p, 4p. The p's are okay because they're the same number as the row number over here, so you don't get the confusion. But you got to remember here, when you're going across this 4th row, this region here is 3, quantum number 3.
So titanium would have like N equals 3?
That's right.
Okay.
And osmium would be 3, 4, 5, and equal to 5. Or if I look over here, that's 6. 1 less than 5 is 6. 1 less than 6 is 5. So you can get them that way. But for me, I just remember this is 3D and others go up by 1. This is 4F and the others would go up by 1. This is 2P and the others would go up by 1 each case. So that's a quick way to do it. Yeah. Okay, now let's see, what are you looking at? You need to be looking at the quiz again. If all of you had a copy of the quiz, I wouldn't have to go back and forth like this, but I'm not sure everybody does. How many unpaired electrons would cobalt plus 3 have? So we're doing cobalt 3 plus, and now stop the sharing so you can see it. Okay, so remember a positive ion, we're going to do the neutral first, cobalt. Okay, so we locate it on the periodic chart. Cobalt is this element right here. It's in the d orbital set, and it's the 3d, 1, 2, 3, 4, 5, 6, 7. So it's going to be 4s2, 3d. I'm going to just put 7 in right now. We'll worry about how they unpair in just a second. So 1, 2, 3, 4, 5, 6, 7. So there we go. So we've got the electron configuration. Now I'm going to form the plus 2 ion. So I'm going to take away these 4s electrons first. That'll make it cobalt plus 2. And then I need to get one of these. That's a 6. And that'll give me the cobalt plus 3. So cobalt plus 3 is going to be a 3D 6 configuration. 1, 2, 3, 4, 5. Plus 2, plus 1, 0, minus 1, minus 2. I'm going to put 6 electrons in. 1, 2, 3, 4, 5, 6. Cobalt plus 3 looks like that. This question wanted to know how many unpaired electrons does it have? 1, 2, 3, 4. So it is 4. That's response A on the exam. All right. And you need to see the quiz again. All right. And the answer then is A. And number 12, we are ranking electronegativities of the elements. So, gosh, I really don't want to write on my book. Let me pull this piece of paper up here and sort of copy out the positions. Phosphorus is group 6. So I've got phosphorus is here. It's in group 6. I've got sulfur. I'm sorry. It's in group 5. What am I doing? You know better than that. Okay. It's in group 5. Phosphorus is. Sulfur is right next to it, but sulfur is in group 6. Sulfur is right there. They're on the same row. Then I'm looking at germanium, and germanium is in
Dr.
group
Pearson?
4, row 3. So it's in group 4.
Dr. Pearson,
Yes,
can you put your camera back again?
I'm sorry. Okay, all right, we'll do it. We'll try one more time. Okay, the elements that we were ranking are phosphorus, sulfur, Ge, and Se, germanium, selenium. Okay, so phosphorus is in group 5, sulfur is in group 6. The germanium is the next row down in group 4. Germanium is here. And selenium, sulfur, selenium. Now selenium is right under sulfur, so and in the same row as this one. So Se is right here. Now, the noble gases are over here. This one's going to be the least because it's further away from that row. These two are the same distance from the end row, but sulfur is higher. So this one's going to be the largest. So all I got to do is look on the periodic table, and we should be able to answer. Look on the question, we should be able to answer. Let's pull the screen share up so you can look at it. And okay, now what we said the order was is germanium is the smallest. So that tells me it's either A or D. I can eliminate B and C already. If I ran out of time, I just guess one of these and I got a 50-50 shot at getting it right. Okay. Now, sulfur is the largest. So I'm looking at A and D, and sulfur is in the right place. So I am forced to make this other condition to distinguish between the two. So the next smallest would be phosphorus. See, this is the furthest away from its row. So that would be phosphorus, and then selenium would be next. So it is response D from what we did in the ranking. Okay, now this one is going to deal with the size of potassium and sulfur and bromine on the periodic chart size. Let's go over and stop the share so we can take a look. And now, again on the periodic chart, potassium is way over here. It's in group 1. And it's in the 4th row. And the next one is sulfur. Sulfur is in group 6, 2nd row. Sulfur is let's do it this way. Potassium, so sulfur is going to be over here in group 6, but higher up on the chart. And then the last one is bromine. Bromine is going to be in here. It's below the potassium row, right? Yes. So, what am I looking for? Bromine is down here.
Could you slide your paper up a little?
Yeah.
Thank you so much.
Yeah. Okay, there we go. Now, so this is the relative position on the chart. Notice they're all on different rows. The argument we're going to always make is the one that's further down on the lower row is bigger. So that may not always be the case, but we're going to think that the element that's further down is smaller. And so that would be this one. And the one that's highest up, I'm sorry, would be largest. Further down is larger. Further up is smaller. And we'd expect that one to be in between because they're all on different rows. So if we go back to our screen share, I think we can pick out the correct answer. So sulfur is going to be the smallest, and potassium is going to be the largest, and bromine is going to be, oopsie daisy, wait a minute, what am I doing? Is potassium and bromine on the same row? Yep, they are screwed up. Potassium and bromine are on the same row. So in that case, potassium is, they get smaller going across in the same row. So bromine is going to be smaller. Potassium is going to be the largest. We wouldn't have made that mistake if I'd had a good periodic chart that I could mark on. Okay, yeah. All right, so we're good. Now.
So it gets smaller towards the left side of the periodic table?
Yes, as you go across, unshare here. The order is when you're going across a period, these get smaller going across this way and larger going down this way. The jump from one row to the next going down this way is much bigger than the decrease going from one to the next across a period. So the more important consideration is row size. And in this particular case, potassium and bromine are both on a row further down than sulfur, so sulfur is going to be the smallest. But since potassium and bromine are on the same row, row 4, then potassium is bigger and bromine is next. So we get this one directly because it's higher up on the chart. We get this order by looking on across the row. The rows decrease as you go across. Okay. The next one, number 14, compares the size of calcium +2, sulfur -2, rubidium +1, and strontium +2. So let's just look on the chart. If I get calcium, calcium is right here. When I lose 2 electrons, it's number 18. So it would be argon. So this is an argon core. Sulfur -2. Sulfur is in group 6, 2 electrons. It would be like argon also. Rubidium plus. Rubidium is element 37. Krypton. This is a krypton core. And strontium is also a krypton core. Strontium is the next element across on the periodic table. So it's krypton also. Now, these are going to group themselves into 2 parts. This core is smaller than this core. So these are the smaller. And these are larger. Now, if I'm looking at the size of these two, this one is a +1 ion, and this is a +2. The +2 is going to be smaller than the +1. So of these two large ones, the +1 is the largest. So yeah, Rb +1 is going to be the largest of the bunch. And the next one over there on that side is going to be Sr +2. That's going to be the largest. Now, of these two over here, they're both smaller than that group. But in this group, the smallest one would be the +2 ion. The -2 ion would be the largest. So the smallest would be calcium +2. And then that would put S-2 next. So if I now look back at my screen share, we can pick it out. Okay, so the smallest, oops, I need to go down one row so you can see it. The smallest we said was going to be calcium. And the largest we said was going to be rubidium. So if I'm taking the test, I'm going to eliminate A and D. Calcium's in the right place for these three, but rubidium is in the right place for these two. So I can eliminate A and D. But now I do have to make the comparison for the other ones. And then the next one should be this one, and then this one, and then this one largest. So that's the best way to make the comparisons. And now don't forget, it's not just the charge. And, you know, if you just memorize the charge, you'd say, okay, calcium and strontium are both +2, so they ought to be smaller. And then this would be the largest. No. That's only true if they're all the same noble gas core. I emphasized that in the lecture when we talked about that. The core is what determines the biggest difference. So these two both have a krypton core that's bigger than argon core. So both of these are bigger than either of these. And then within each one of these, you can compare charges. The negative is bigger than the positive, and the most positive is the smallest within a group. Okay. All right, let's go on down. Let's see what we got next. Aluminum, magnesium, silicon, and we're looking at first ionization potentials. Okay, so number 15. Okay, magnesium, aluminum, silicon, and nitrogen. Let's see, magnesium, aluminum, silicon, and nitrogen. And we're comparing first ionization potential. Okay. Let's get so you can see the paper again. Okay, so we're comparing first ionization of magnesium and aluminum. So magnesium and aluminum are on the same row. And what we learned in going across the periodic chart, let's remind ourselves what we got. If we start at 1A, 2A is up here, but 3A is down here. Then we got 4A, 5A, but 6A is down here. And then 7A, and then 8A for the noble gases. So this is going across the period. This is group 3A, and this is group 6A, that you get the drop. Okay, so aluminum is going to be less than magnesium, and these are metals. So both of these are going to be smaller than the non-metals. So aluminum is going to be the smallest, and then magnesium is going to be a little bit bigger. Remember, I'm looking at this one, that's aluminum. This one is magnesium. Okay, and now we are looking at silicon and nitrogen. Now, nitrogen is up here and silicon. Nitrogen is exception. It's not on the same row with these others. Magnesium, aluminum, and silicon would go in the order they're supposed to. This would be silicon right here. But I'm not putting nitrogen on here. It would be in here, but it's in a row above it. So it's going to even be the highest. So they're still going to go in that order. Because nitrogen is a smaller atom than is silicon. So it's going to be a higher ionization potential. So if I go back and share with you, we should be able to get the answer for it. Okay, aluminum is the smallest, then magnesium, then silicon, then nitrogen. It would be D. Now this one, we want to go to identify the elements from its first ionization potentials. So I want you to look at the numbers. The difference between these two is what, 900 here. So it's about 800 units here. But from here to here, it's 13,000 difference here. Between here, it's about 7,000. So the biggest jump occurs between the second and the third. That big jump, 3, means this is a group 2 element. So if I'm looking on the periodic chart, we're looking for an element that's group 2. Okay. I want to stop the share. And now, so we said we were looking at group 2. And group 2 elements, we've got beryllium, and then we've got boron is over here. We've got carbon, which is here. We've got nitrogen, which is here. So it has to be beryllium. It's in the group 2 position. So beryllium is the correct answer. Now remember, when you're looking at this pattern, you see first ionization potential, second ionization potential, third ionization potential, and fourth ionization potential. These are what we've got here. And this is that big gap. First, second, third. The big gap occurs here. So this is the group number. If this one had been down like this and that one the big one, then this would be 4. It would be a group 3 element and so forth. So you always look for that big gap, and whatever ionization potential that one is, the group number is the one before it. Because when you did this one, before that one, you formed a noble gas. And group 2 needs to lose 2 electrons to get to the noble gas. If it loses a third one, it'll take a tremendous amount of energy. So this one is number 16, is B. I need to share a screen with you again. Okay. And which of these species below has the same Lewis dot structure as an oxygen atom? Well, oxygen's in group 6. So I got 1, 2, 3, 4, 5. Oopsie daisy. Now you got it. Okay, here we go. We got 1, 2, 3, 4, 5, 6. So I'm going to have 6 valence electrons in this particular atom. Now, we'll get to if I've got to compare the other elements. Chlorine is in group 7. So I would do 1, 2, 3, 4, 5, 6, 7. Now, but a +1 ion would remove one of these electrons. So let's suppose I took this one out. Then what have I got? 2 pairs and 2 unpaired. So Cl plus is going to have the same shape as that one does. If you try the others, they don't work. but that's the one that would work for that. Okay, let's move right along. 18. Number 18. How many valence electrons are present in the hypothetical SO2 2+? So we're looking at 18. It's SO2 2+. All right, so let's jump over here. Sulfur is in group 6. Oxygen's in group 6, and we've got 2 of them. And we've removed 2 electrons. This would be 18 minus 2 would be 16. So how many valence electrons does it have? It has 16 in it. That would be the correct answer for this one. That one is intended to raise the average. Okay, all right, I want to get you back to here. All right, now, how many lone pairs of electrons are there in OSBr2-? 19 OSBr2-. Okay, let's go back over here so we can see the pad. Okay, so oxygen is in group 6. Sulfur is in group 6. Bromine is in group 7. And I've got 2 more electrons for the negative charge. Okay, so 6 and 6 are 12, 7, 19, 20, 7, 13, 14, 15. Something's wrong here.
I think there's
It should-
two of the bromiums. Bromine.
Oh, it's Br2. Thank you. OSBr2. Okay, so I need to multiply that by 2. The reason why I knew that was wrong is you're not going to have an odd number of electrons. We're typically not going to do those molecules because, frankly, they are not very stable. You can make them, but they're typically not very stable, and they are very, 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 very dangerous to us. If you get an odd electron molecule in your body, it's what's called a free radical. And it will attack the next thing it hits and jerk an electron off of it. And when it does that, it leaves the odd electron on the other molecule. And the other molecules will keep doing that until they bump into each other and form bonds to get rid of that odd electron. And that can happen in a DNA. And when it does it in a DNA, that's a gene mutation. And if it happens in certain regions on the DNA, it'll cause cancer. So these are very, very dangerous compounds, free radicals. And some nitrogen gases like NO. NO is a very important molecule to our bodies. We need some in there, but nitrogen has 5 electrons, oxygen has 6. It's an 11 electron molecule. So it can do some bad stuff to you. 7, 14, 20, 26, 28, I guess would be right now. 12. Yeah, 28. We got 28 electrons. We need to divide that by 8. That's 3. And 24. Subtract 4 from 8, leaves 4. And divide the 4 by 2, the remaining electrons by 2. So our VSEPR notation, if we needed it, is AX3E2. But we want to know how many lone pairs. We got that answer right there. The number of lone pairs is 2. And let's see, I guess I need to share screen with you again. Number 20. How many total valence electrons are in a species, molecule or ion, that has a VS EPR notation of AX3E? Oh my goodness. This would be easy. We just did it, didn't we? Let's stop the screen share. And so we just did that one, so we know it's 28 electrons. So we got the answer to that one already. That would save you a lot of time. What if we didn't? Then we would take this, and the way we got that was we took the valence electrons and we divided by 8. So if I take 3 times 8, that's the number of electrons coming from this. I had 2 pairs, and each pair is 2. So I need to add 2 plus 2, or 2 times 2, same thing. So 24 and 4 would be 28. So we get 28 this way as well. So if this had been something we hadn't done up there, then that's the way you do it. You take this number times 8 and this number times 2, and then add them all together. And that'll give you the answer. Okay. "21. How many octahedral resonance structure are there in NO?" I wrote it that way because I wanted you to bond it that way. I didn't say N2O. That's the formula for the compound. But I wanted you to bond it in this direction, so or in this order. So I've got N, O. Let's stop the share, and now you can see what we're doing. Now, how many resonance structures, octet rule structures, can we do with this one? Well, this is 5 electrons. This is 5 from group 5. This is 6. This is 16. So I've got 16 electrons. I'm going to take the 16 and divide it by 8. I get a 2. And 0, and 0 divided by 2 is a 0. So there's no lone pairs on this molecule. So what I'm going to first do is put in this one connecting bond first. We'll have a name for those later. We call them sigma bonds. It's the first electrons you put in that just bonds everything together. They're what we call framework bonds. And we had 2 of them from here. We had no lone pairs, and that is crucial. Don't put
Dr.
any lone
Pearson?
pairs on the nitrogen. Okay?
Dr. Pearson,
Yes.
why are there 2 N's when in the example there's just an NO plus?
I'm doing number 21.
Oh,
instead
okay.
of
Sorry about that.
22. Yeah.
Okay.
Yeah. Okay. I'm back to it. Okay. Now, so I can't put lone pairs on the central atom. The only way I can make an octet is put double bonds or multiple bonds here. One of the things I could do is put a double bond on each side. Now that gives me the nitrogen with 4 electrons around it. That's 8. It's an octet rule structure. That gives me oxygen needing 2, and this nitrogen needing 2 pairs over here. Now, if I add them up, 2, 4, 6, 8, 10, 12, 14, 16, it does check that that is one of the structures. There's another way to do that. Instead of, let's put the framework back in we had. Instead of putting the 2 bonds on one on each side of nitrogen, I could put one on both of them on one side. That would give me this structure, and it would give me this structure. And now we still work. We've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8, 10, 12, 14, 16. This also checks. So this is another structure. Another way to do it would put the triple bond to the oxygen and the single bond to the other nitrogen. And that would give me this structure. Now, how many different structures do we have? Well, in this case, we do have 3. This has 2 double bonds. This one has a triple and a single, but the triple is between the nitrogen and nitrogen here, and it's between the nitrogen and oxygen here. The part we didn't finish in the lecture today would tell us which of these would be the best one of the possible resonance structures. So there are 3 unique ones. Now, I didn't do it here, but let's just suppose I had a molecule like this. Now, this isn't correct, so I'm just using this as an illustration. But suppose I had a structure like that, and I came out with that structure as a possible, and that structure as a possible, and that structure as a possible. Now, these 2 are really the same. They are resonance structures, but if I want to get this one down here, I just take that middle one and turn it over, and it's the same structure. So in this case, there would only be 2 unique structures. There would be this one and this one. And again, if you describe these 2, you describe them the same way. Here you wouldn't. You say this molecule has a triple bond between the nitrogens and a single bond to the oxygen. This one has a single bond to the nitrogen and a triple bond to the oxygen. That's 2 different descriptions. Describe these 2. This one has a triple bond to the oxygen and a single bond to the oxygen. This one has a triple bond to the oxygen and a single bond to the oxygen. See, I described them the same way. So they're the same structure. So this one would only have 2 unique resonance structures, where this one has 3. So I wanted to point that out to you because you do have to be kind of careful. If the question asks you for total resonance structures, you'd count 3 for all of them. But if it asks you for unique resonance structures, there would be 3 for this one, but only 2 for this one. Okay? And I've done it both ways. Okay, let's go back. All right. Now, which of the following is not an octet rule structure? So we want to see, can I draw a structure from these that is octet rule? And unfortunately, I think we sort of have to work each one of these individuals out. So let's pull it off here so you can see my screen, and then I can see them. I've got NO+. Can I make an octet rule molecule out of that one? Well, nitrogen is in group 5, oxygen is in group 6, and we've lost 1 electron, that's 11. This would be 10 electrons. So I can get N, and I have 10 electrons, minus 1 rather. 10 electrons, 10 divided by 8 is 1. 8 and 2, 2 divided by 2 is 1. So I'm going to get, if I'm making the nitrogen, that one, I've got this kind of structure. Now, to make an octet here, I put 3 bonds here and a lone pair here. Let's see, what have I got? 2, 4, 6, 8, 10. That does work. So I can make an octet rule structure. Of course, this is +1. I can make an octet rule structure out of that one. Now, this is ionic, so let's see, Mg3N2. Magnesium typically forms a +2 ion. Nitrogen in group 5 would form a -3. So if I made that a -3 and this a +2, I would get this formula. Magnesium would have the same, magnesium +2 would have the same electron configuration as argon. So this is argon. All the noble gases have 8 electrons around them. Nitrogen -2, nitrogen -2 would be neon. And neon, all the noble gases except helium have 8 electrons. So that one is an ionic compound that does obey the octet rule. Let's do iodine tetrachloride ion minus. Okay, let's do the math. There's 7 electrons from this chlorine, iodine. I've got 4 chlorines, chlorines in group 7, and I'm adding 1. So this is 5 times 7, 35, and 1 would be 36. So this is a 36 electron molecule. 8, and that would be 4. 4 times 8 would be 32. Remainder 4, and that's a 2. So it's an AX4 E2 type molecule. So that's 6 things attached to the central atom. So I'm going to put iodine in here. And I'm going to put 2 lone pairs on. They're going to go opposite each other. The first one will go here, or any one of the places, but the other one has to go opposite it. It go here. And I'll put the 4 chlorines on here, and 4 chlorines on here. I can put the lone pairs around everybody, but this is not octet rule. 2, 4, 6, 8, 10, 12. This has got 12 electrons around the iodine. Now, I told you you can have more than 8 around any atom except the first row. First row can't do that. But this molecular ion can form. Yeah, let's do that. 22. The last one was XeO4. Can I make an octet rule molecule out of this one? Well, we've already got the answer, but xenon is in group 8, and oxygen's in group 6, and we got 4 of them. So 24 and 8 would be 32. Divided by 8 is 4. 32. 0 divided by 2 is 0. It's an AX4. So sure enough, Xe can have 4 atoms of oxygen attached to it. And I can put my lone pairs on all the way around and add them all up. That'll come out correct. But the important thing is right there. Xenon has 2, 4, 6, 8 around it. It is an octet rule molecule. So this is octet rule. It has 8 electrons around the central atom. So all of these work except iodine, tetrachloride ion. That one does not. Okay. That one takes a little time unless you happen to try the correct answer first. I'm not usually that fortunate. Some of you will be, because what I do is I have each question randomized in the order of the responses. So somebody is going to have that as the first, as A. Okay, all right. Nomenclature. Now, these are supposed to be the gimme points, okay? Okay, let's see if they are. This first one, top share, I can copy it over here so that we can look at it. Okay, so we got CO and H2PO4. Right, 3. Okay, so that's the formula of the compound. I'm going to look at the anion and I'm going to say, okay, this anion is called dihydrogen phosphate. So it's a polyatomic ion. I've already got that part of the name. It's dihydrogen phosphate. Now, the dihydrogen phosphate carries a -1 charge. Phosphate itself has 3, 2 hydrogens plus 2. -3 plus 2 is -1 for the dihydrogen phosphate. There's 3 of them, which means cobalt is +3. So the correct name is going to be cobalt Roman numeral 3 dihydrogen phosphate. And that is response B on the test. Okay, and ammonium dichromate, number 24. I could probably just leave that over there where I can see it. And then, okay, I want the formula, number 24, is ammonium. Ammonium is NH4 plus. And dichromate is Cr2O7 2 minus. Now, you memorize that. It's a part, but let me show you how it's actually bonded, and then it'll make sense. If I did chromate, it's CrO4. 2 minus. If I want to make dichromate, this oxygen gets shared with another chromium. So dichromate, you've got 2 chromates sharing an oxygen. It's going to be Cr2O, 1, 2, 3, 4, 5, 6, 7. Cr2O7, negative 2. So dichromate is this structure. So if I'm going to make the ammonium compound, I'm going to make NH4, 2, Cr2O7. That's ammonium dichromate. Now, notice NH4. Notice that it is not diammonium chromate. Don't name it that way. Dichromate is this one. So it's not diammonium dichromate, it's just ammonium dichromate. I don't need that prefix because dichromate gave me the formula and charge. From that, I knew I had to have 2 ammoniums to balance the dichromate charge. This is +2 and this is -2. With 2 of them plus 1 and 2 of them is +2 with a -2. So that's the formula. Okay. All right. So we got the answer. And so it's the first one. It's 2 ammoniums with Cr2O7. Now, number 25, it's nomenclature also. I'm naming an acid. You know, this is an aqueous acid, HMnO4. I'm going to look at this and I'm going to remember permanganate. And permanganate has a -1 charge, so that's why there's 1 hydrogen attached to it. But if I've got this ion correctly, all I'm going to do is I'm going to take off that ATE. I'm going to put IC and add the word acid. So this compound is permanganic acid. So all of your anions are going to end in ATE or ITE. And if it's the acid hydrogen compound with them, if it's ATE, just change it to IC. If it's OUS, which is the other one you'll get, ITE, I'm sorry. If it's ITE, then you change the ITE to OUS. So in this particular case, it's permanganic acid. Okay. And number 26 is going to be hypobromous acid. Okay, so acid. All right, so let's let you see my paper again. So I want hypobromous acid. So what I'm looking for, if this is OUS, I'm looking for hypobromite ion. Okay, hey, I didn't learn that one. But I did learn hypochlorous or hypochlorite ion. It was HOCl minus, was hypochlorite. I memorized that one. So you can replace the chlorine with bromine and make hypobromous acid or hypoiodous acid or hypofluoric acid and so forth. So hypofluorous doesn't exist, by the way, that one doesn't. But so HOBr minus ion, that's the ion. And the, well, that's hypochlorite. And this would be hypobromite, hypobromous acid with the H on it. So it's HOBr. So that one's fairly easy to get. But remember now, on the 31 polyatomic ions I've given you, if you get a stump like that, just remember you can replace any element in those formulas with something else in the same family and generate an analogous name. And so that's why I can keep the list to 31 ions, because I can make a lot of the others from just those. And now we need one more VSEPR, so 27 is PF4 minus, and we want to get the VSEPR notation for it. Okay, so phosphorus is in group 5 on the periodic chart, so it's got 5 valence electrons. I've got fluorine is in group 7. I've got 7 valence electrons for fluorine, and I've got 4 of them. And I need to add 1. So 4 7 is 28, 29, 34, right? Divided by 8, that's 4. That's 32. And 2 and 2 divided by 2 is 1. So it's AX4 E or AX4 E1. And that's that's answer number A on that. Okay, now on the practice exams, I just gave you 26 questions. There's 27 questions. There's on exams, there's going to be an extra one, like the practice quiz usually has 7, and the exam practice a real quiz has 8. The practice exam, I've revealed 27 of the 30 questions. The other 3 will be something I want to emphasize or something that comes from lecture. They're the surprise questions, but there should be at least 3 on there somewhere that really just kind of fall out. They look like something everybody who paid attention in lecture would know. So it's not going to be some new problem I'm going to spring on you. It's going to be something that I emphasized in lecture that maybe isn't covered by those first 27 questions. Okay, how we're doing? Okay. Okay, let's stop the share, and I'm going to stop.